right, let's take a look here. So this first problem, everybody should have gotten this 3/4. We talked about that. So when I go to draw them in, go like that. And then what is that? And finally, there. So those are the 4 inputs I should use. And it looks like it's going to be probably a little bit of an underestimate, right? This fills this in, but not completely. So I know my answer should be a little under what it's supposed to be. It looks like it. So then the area is approximately delta x times f of negative 1.25 plus f of negative 0.5 plus f of 0.25 plus f of 1. So it's 3/4 times, and then whatever all these are. Negative 1.25 squared plus 2. What do you guys get for that? 5/4, 25/16. 25/16 is... Anybody got that at all?
3.5625.
3.5625 plus f of negative 1/2, which will just be 2 1/4, so 2.25, right? I think. Plus f of 1/4, which will be 2 1/16, which is like 2.06 something, maybe 2.0625. And then f of 1 is going to be nice. It's 3. Yay. And when you plug all that crap in your calculator, you get something. What do you guys get? 8.15625. So what do you guys get? Do you guys remember how to check that in your calculator? Calculator. Let's first put it in there. So if we put x squared plus 2 in there, poor little dude. There you go. And then I graph in. Let's hit zoom 6, graph that nice parabola. And then I tell it second trace to get to calc. Number 7 is the area from, what was it, negative 2 to 1. I get 9. So yeah, it's exactly what we thought. It should be a little bit of an underestimate, but pretty close, because it's a nice function. I like it. That's a beautiful thing to remember. It's never good enough just to get the answer from this, but shit, it's great to check, right? So if we do this, we're going to do this all the way out. Well, let's first set this sucker up. What's delta x going to be in this time? So, real quick, the right way to look at this is the very last thing I worry about is this dude. Which means how many rectangles am I using? N. I'm going to eventually let it go to infinity, but when I first start to set this up, I'm using n rectangles. Which means the width is now going to be 3 over n. Which means xi is going to be, starting at negative 2, plus I steps. I like it. Which, real quick, let's double check. What was x2 up here? Here's x1. This is x2. Right? And what's this say it's supposed to be? Negative 2 plus 3 times 2, because now I want the second one, divided by, for this one it was 4 rectangles. So what's negative 2 plus 3 halves? Negative 0.5. Yay. So this expression shows you how to figure out all these things for any number of rectangles. That's why that expression makes sense. Okay, I like it. So what's f of xi? It's just going to be take this and shove it into here. So let's see what I get. Let me write this like this. 3i over n minus 2 squared plus 2. That's what f of xi is. Let's go ahead and kind of work that out a bit. You didn't have to for this problem, but we're going to need it for the next step anyway. Well, let me go ahead and write down what this looks like. So limit n goes to infinity, become an infinity. I equals 1 to n. F of xi is this dude. No idea why I made that 3 so big. Times delta x. And the reason I put these big ass brackets around it is just to make sure that everybody knows that all of this is inside this summation symbol. I like it. I like it. So if I multiply this stuff, and let me give myself some more room. You do it, Jeff. All right. So if I multiply this out, let's see what happens. So number 2 just said to stop there, but I said let's go ahead and do this one all the way out. So multiplying this business out, I'll get 6in, so I get 12i over n. Is that cool? Foiling that bad boy? Plus 4 plus 2, and all of that times 3 over n. I like it. So then you get so you get 27 I squared over n cubed minus 36i over n squared plus 6 times 3, 18 over n. I like it. Do you see how the I stuff is always the degree less than the n stuff? That always has to happen. Just like with limits, limit definition derivative, what always had to happen? I had to be able to kill the h's. So if you got to the point where you wanted to kill the h's and you had something without an h in it, that was you made a mistake. You got to go back and refoil or something. You guys remember that? So the uglier the function gets, I would never try to do this process with a square root. I don't even, if you just think about what this would look like with a function as a square root. Or tangent. Can you imagine trying to do this with tangent? Just imagine that. Oh my God. So that's why, just same thing with derivatives. We can't do some limits of things. So that's why we do a few of these, and then we start to develop a shortcut. Now, let me see. Let me go ahead and break this up. I'm showing so many steps. I'm going crazy. So this is where you need to know. I'm not going to make you memorize them. I'm going to give them to you always. Let me see if I remember. Oh, shit. What am I talking about? So the 27n cubed, are you guys, depending on if you've done these yet or not, you should get to the point where you're used to those just coming out, because the summation symbol only sees I as a variable. That's a constant that I can factor out. And what's the sum of I squared? I think it was n plus 1 times 2n plus 1 over 6. Is that close? Oh, I got it right here. Oh, I'm missing an n. Okay, yeah, it's got to be a cube, Jeff. N times n plus 1 times 2n plus 1 all over 6. That's what the sum of I squared is. You guys with me? I take that out. What's the sum of I squared? Well, I know the sum of I squared is this business. So I just put it right there. Minus 36 over n squared comes out. The sum of I is just going to be this one. This one I know because it's a nice easy one. And the idea is so beautiful. Can't help but know that one. And you're going to get to the point where you know how this one works. What's the sum of 18 from 1 to n? So the 1 over n comes out. What's the sum of 18 n times? And that, of course, is where we come up with the word times for multiplication, right? Sum of 18 n times is 18 times n. Add 18 up twice. What's another way to write that? 18 times 2. So add 18 up n times. So it's 18 times n. So here I'll do this one. Dead. So that piece is 18. Yay. Kind of working backwards here. 36 divided by 2 is 18. What's the limit of this as n goes to infinity? What's this limit? What's the degree of the top? Squared, yeah, 2. Degree of the bottom is 2. The coefficients are 1 and 1, so that limit is 1. So that's just 18. What about here? 27 over 6 is 9 over 3. What's this limit going to be here? Well, the degrees are the same. What's the coefficient of the top? 2. And the coefficient of the bottom? So that limit's going to be 2. And of course, that's that good old shortcut for horizontal asymptotes from pre-calculus. Why is the limit not written anymore? Because I just applied it. I don't need the limit statement anymore. I've applied it already. And what do you get here? We get whatever the hell that is, because these cancel. So 18 over 3. Why did I put 9 over 3? That's so smart, Jeff. 9 over 2, there it is. So it should be 9. Is that cool? 27 over 6 is 9 over 2. That limit is 2. It's 9. And if you remember, that's what we got. That's what we got from the calculator that basically does a modified version of this to get its area. Okay, I like it. I like it. I think I want to bring to you, I'm not going to do it right now because it might drive you even more insane than I do on my own already. But if you do this whole process not with, where to go? Here. Without putting a definite range in. If you do this whole process where the range is 0 to x, and you do this whole thing, so what would change? The width would be x over n, and so forth. What you end up with is the antiderivative of this function. It's really cool to see. So I think I'll bring a worked out problem like that. Just in case, if you don't want to look at it, you don't have to. Because we're going to prove that today, that connection. But it is nice to see this process end up with the antiderivative. And do you guys understand why that's so freaky? What does this process do? It finds the area under the curve. And then it ends up somehow being related to the antiderivative of the function. If you think about it, it kind of makes sense, but it's not immediately obvious. All right. So since I'm talking about antiderivatives, it kind of makes sense. Let's do this last one real quick. What do I put here when I'm finding this? Big ass f of x, yeah. And what's this antiderivative going to be? Good. All right. So I'm not going to take off, I might take a point off. Normally, if you do it a couple times, you take a point off. So you're not going to die if you forget the plus c, but it is very important for that to be there. It's got to be there. And now this guy's same kind of idea that happened here has to happen here. Cosine comes from sine, right? But why is that not right? It would have an extra 4. I want to kill the 4, so I put this over 4. Right? If I just had this, its derivative would be 4 cosine. I don't have 4 cosine. I want to kill that stupid 4. Okay, kill the 4. What's the antiderivative of 1 over x. Beautiful. Become a straight line. And then, of course, yeah, so what I did here was I took that negative 2 out of the way. It's just a constant. And then I have 1 over x. Because people let that 2 mess you up. It's just a stupid constant. It needs to be there, but it's nothing I need to consider. It's really, I keep saying that same kind of thing. You can realize that a lot of what we're about to do is going to be a lot easier. Okay. So I finally want to do this. And again, I know some of you guys have had some calculus before, so if you know integration fully, well, shit. I wanted to stay up on the overhead. Oh, here we go. I got some paper. That's the paper I want to use. Darn it. I got it. Do I? No, it's double sum. All right. Well, too bad. Okay. So now we're about to finish up section 5.3. Do the second part of the fundamental theorem of calculus. All right, this is not like history of the world part 1. There is a part 2. Fundamental theory of calculus part 2. So I'm going to start somewhere a little weird, but then we're going to make this beautiful connection. So let's start somewhere just defining a few things. So if I define g of x to be this, like we did before. Right? So recall that we've seen that before. G is kind of like the area function. F-talk part 1, to go back to what we did, it led us to this reality. That since g prime of x is f of x, therefore g of x has to be this. Let me stop there for a second. So F-talk part 1 is all about taking the derivative of this new function. Really, anytime we have a function that we haven't attached in calculus before, the first thing I want to do is, how does this thing work with derivatives? So we made a new function. We've never had this function ever before because we didn't even know what the shit this meant before. What does this symbol mean again, by the way? Just tell me what the name is. This is the integral. But what does that symbol represent? Infinite sum. That's why it's a big ass S. Because like it's an S, but it's infinite. So, yeah, good job, creative people in the past. So I've developed a brand new function. F-talk 1 talks about what the derivative of that new function is, and it becomes just f evaluated at x. It's kind of cool. And in fact, before we go too further on this, let's do an example real quick of F-talk 1. So if I have g of x, bless you. So a little side note. Here's what F-talk 1 really looks like in action. What is g prime of x going to be? So here's where people go a little insane. I want you to really realize, now we're about to make this connection, but now it really makes sense why this is. This is related to the antiderivative. So if I take the derivative of the antiderivative, this should just cancel, basically. Does that make sense? So it's all like cubing something that's been cube rooted. They should cancel each other. So what I end up with then is just this evaluated at x. That's it. So that's the one piece of this that you have to go back to the discussion about F-talk 1 to see why it makes sense. It doesn't even matter what this is. And once we finish today's discussion, I'll come back and remind you, and then you'll go, oh, that's why it doesn't. If I would have put a 7 here, same answer. And negative 18 billion and 2, same answer. Because this would relate to a constant, and when I take a derivative, it just goes away. Now, here's the next kind of level to this. You're going to see this in this homework. So that's number 1. What if I had this? If g of x is the integral from negative 17 to x squared, what you got, Jeff? Hyperbolic cosine of 3 over the square root of 4 minus t cubed. Sure. And then I say, what's g prime of x? So this is where it gets really, really weird. Where's my input for this function over here? So if I said, what's g of 7? Where would you put the 7, of course? Up there, right? So it would define from 2 to what? 2 to 7. So this is the cumulative area function, really. So what kind of property of derivatives do I have to use because there's an x squared there instead of an x? What do I do when there's an x squared inside of something instead of just an x? What rule do I have to use? I think I heard it whispered. I heard it on the wind. So okay. Side note. What's the derivative of this function? Yeah, the derivative cosine is negative sine. Negative sine of this business. But then you have to multiply by the derivative of the inside. You have to use chain rule. Whenever the inside piece is more than just x, chain rule comes in. What's the inside piece on this function? X squared. Down here, what did we do? The rule for cosine is its derivative is negative sine of stuff. Then I worried about the chain rule piece. So what's the rule for the derivative of this type of function? It's going to be this evaluated at that place. You're going to just basically kill this. So the first step is just plug x squared in, but then you have to multiply by the derivative of the inside. That times 2x shows up the same way it did for this guy. So this step right here is just a rule. How do you take the derivative of an integral of something? It's that thing evaluated at that endpoint. Oh, the shit, that endpoint is some more than just x. Oh, I've got to do frickin' chain rule. So if I would have made this x squared, I would have just had an x squared here times a chain rule piece, times 2x, the same way. So the chain rule doesn't give a crap how funky your function is. It just says, I'm going to be here because your inside's not just x. I'm going to show up. Okay, maybe. All right, so coming back from the side note. So now watch this. This is where things get really neat. Maybe I can do this now on, where'd it go? Did I already use it? I did. Nice up. No paper. You have a piece of paper to borrow real quick? So I can just stay up on the overhead. See motion. All kinds of rounding points, corners, thing. All right. So now watch this. So we have all of this set. We talked about that first line. Last time we proved the second line. And then the last line is me. What did I do to get from here to here? I'm sure you guys can already see that. What did I do to get from here to there? I undid what? I took the antiderivative, right? Took the antiderivative. The antiderivative of g prime is just g. That's amazing. And the antiderivative of little f is big ass f. And then, of course, plus c. So now, here's what's really cool. And again, what's really interesting is when you get further in math and you look back at stuff like I'm about to do, you realize it was discovered in a different order than what we present. But of course it is. The way you discover shit doesn't make sense when you try to, you go, all right, now how do I tell somebody else? I got to reorganize this. So the way we teach doesn't match the way with history all the time. But that's why this first step looks a little weird. So let me see, what is this? Let's investigate what the shit that is. Why, Jeff? Because. Makes sense, eventually. This is what I want to investigate. I want to investigate that. What is that in terms of G? So what is f of b? Well, okay, what's f of x? Is this, right? Let me see if you guys are cool with this. Can I? Let me see if you guys are cool with this. It doesn't really matter, but can I just turn this around, make this a minus c or something? Is that cool? Just have to have the plus c somewhere. Is that all right? How are big ass f and g related? They're offset by a constant. Maybe. So what would f of b be? It would be g of b plus c. What would f of a be? G of a plus c. That's what this leads to. So what is f of b minus f of a? It's going to be g of b plus c minus g of a plus c. What happens to the c's? They cancel. So I get f of b minus f of a equals g of b minus g of a. All right, that's neat. What was g of x, though? What was g of something? What would g of b be? Where do I put? So what's g of b? Where's b go? Right up there. Yeah, so g of b is integral a to b f of t dt. So g of b is integral a to b f of t dt minus, what's g of a going to be? The integral from a to a f of t dt. Bless you. What are these? Antiderivatives. What are these? Areas. So we've got a connection between the antiderivative of a function and the area under that function. Now, can somebody help me out? This piece is kind of silly. What's the area under f from A to A? What's the area? So if I had a rectangle that went from 0, or let me see, from 7 all the way to 7, that was the base of it. What's the area? 0. It's got 0 width, right? So this is 0. Because you're finding the area from A all the way to A. There is no area under that. It's a straight line. That has no area. So what we have just discovered is that to find, now look what we just figured out. Okay, and I know some of you guys kind of gave up on the way, but what we've just discovered is this is a statement about the area from A to B under this function, or between that function and the x-axis. This is the difference of two antiderivatives. So now we've connected area to antiderivative. So what do I do to find this for any function? The area from A to B under, and this piece you just got to get. The only reason I needed t's in here was because I had an x here already. So f of t dt is the same thing as f of x dx. It's the same thing as f of m dm. The variable doesn't matter which variable you use. I'm going to go back to x because that is what we almost always see. So the integral, the area from a to b under this function is equal to the antiderivative evaluated at the top minus the antiderivative evaluated at the bottom. So let's try this out. Let's do that one we just did. Where'd it go? What was the... Here we go. So we did x squared plus 2 from negative 2 to 1, right? Let's try this out. So the integral from negative 2 to 1 of x squared plus 2 cool. That is what this translates into, is the integral from negative 2 to 1 of this function. And now you realize this is all the function heights, these are all the widths, that's just the areas. And this means an infinite sum. So it really is the same process, but now we've got a shortcut. What is the antiderivative of x squared plus 2? What's the antiderivative of x squared plus 2? And the antiderivative of 2? 2x. Why do I not have to put the plus c? Because in this proof we showed that the c's are going to do what? Cancel. So when I have what is called, do you see why this name makes sense? This is called a definite integral because there is a definite range I'm interested in. If I had an integral without those, that just means find the antiderivative. So here's the notation that is most commonly used. I have to evaluate this function between negative 2 and 1. So look back at what we discovered. To find the integral under a function, it's just the antiderivative evaluated at b minus the antiderivative evaluated at a. So what I'm going to do now is plug a 1 in, evaluate it at 1, minus evaluate it at negative 2. I forgot let me make this really clear. There. Try to anyway. So put a 1 in there, minus what you get when you put a negative 2 in there. I think if I remember correctly, this is supposed to come out to be 9, right? Let's see what we get. We get 1/3 plus 2 minus negative 8/3, so plus 8/3 minus negative 4, so plus 4. Is that cool? And that's just numbers. I mean, got to eat that stuff up. 1/3 plus 8/3 is 9/3 is 3, plus 2 plus 4 is freaking 9. Now look at this. This work is the same thing as this work. It's the shortcut to this. This is finding the area directly. Before we had the connection to antiderivative. Now we have a connection to an antiderivative. Beautiful. What's the only way this process could be difficult is if this function is hard to find an antiderivative for. Some integrals are actually completely impossible. Yeah, almost completely impossible. So if you get to Calc 2, you can actually work with some of these things that you can't do. So what's a very basic example of something I can't find an antiderivative for? We've actually talked about this before. Like something like this. So that statement now means find the antiderivative of this. That's what that means. Without any inputs, it just means find the antiderivative. Why can I not find that guy's antiderivative? What should any E thing, where should it have come from itself, right? But the minute I write this down, what's supposed to be here for this to work? What's the derivative of this? What's the derivative of this? What's the derivative of e to the x squared? What's the derivative of e to anything? E to that thing. times what rule comes in? Chain rule comes in, 2x. So do you see exactly what we're missing here for this to work? I want this to make complete sense, because if I'm missing a constant, that doesn't matter worth shit. I can always balance that out. We'll do another example where I can show you that. I can't balance this out. What am I missing here? 2x. And it's not there. So this is a integral. This is an antiderivative I cannot do. It's not doable. It's the most basic example of a function I can't take the integral of. It's crazy. Let's try one we can do. It's got a little bit of this flavor of what I'm talking about. Why is this one doable? Why could I find that guy's antiderivative? Well, we'll focus on this piece. Where would that have come from? Where would cosine of something have come from? Sine of something. Let me check what I got so far. What is the derivative of this? Do you remember we talked about it? How do you check your integration work? You kind of take a guess, kind of check where it is. There's really nothing wrong with that, to be honest. We will develop, starting today, going into the next time, a more formulaic way to do what I'm doing right now. But I want you to get a feel for how to just see how this works. Cosine comes from freaking sine. There's no question. What is this guy's derivative? What's the derivative of sine of x squared? Cosine x squared. So, sure enough, is that what's in here? Is that what's in here? Yes. So I'm done. I figured out the answer. Why was that integral relatively easy? Because it had the chain rule piece there that it needed already. It was already there. Maybe. Yes?
How come you do the plus c? Doesn't it?
Only if there are definite inputs here.
Oh.
Then I have the subtraction of those two and the c's cancel.
Okay.
This symbol by itself means just the antiderivative. That's all it means. So the integral symbol by itself, with no numbers on it, means find an antiderivative. So that's another way to ask that question now. I like it. So let me do this. I've got another little sheet. You know me. Just a few problems to try. The first ones are f-top2, the ones that have numbers on the integral. So we find the antiderivative and plug those numbers in. And then the second one is no limit. So you have to have a plus c. It just means find the antiderivative. Don't work on the side that says 5, 5. Use substitution. Don't worry about that yet.